Like if you could do one thing, like what is the core central thing that you need to know in order to do this question? Yeah, what is d dx of x to the x? That's what this entire question comes down to. Do you agree? Yeah. If you can do that, then the rest is just probably, you hope, relatively straightforward derivatives and limits. So have you ever seen that derivative before? Have you ever done something like this? No. You have to use logarithmic differentiation. Oh, well, let me just show you, and then you can tell me if you've seen it before. You say y is equal to x to the x, okay? So the natural log of y is equal to the natural log of x to the x. Which is x. Which is, so you know that ln of y is equal to x ln of x, correct? So what can you do at this point? If you wanted to take this derivative, you could do what kind of differentiation? What kind of differentiation can you do? What's it called? Excuse me. Implicit differentiation. Good. So you implicitly differentiate both sides. What does the left side become? 1 over y prime is equal to, and then what do you have to use on the right? Product rule. So the derivative of the first times the second plus the first times the 1 over x. So do you agree with that right there? Yes. So let's just simplify a little bit. We have 1 over y prime is equal to 1 plus ln x. Do you agree with that? Yes. Okay, so what do we know y prime is equal to? Y times 1 plus ln of x, right? But what does y equal, everybody? Cheap tricks by Mr. Seamon. Okay, y equals that. So you have y prime is equal to, what was it? X to the x times 1 plus ln x. But what does, oh, y is equal to x. Oh, wait, so now what do we know? X to the x, let me write that a little more neatly. So now for you know that x prime is equal to x to the x times 1 plus ln x. Because what does, look, if y is equal to x to the x, so y prime is equal to the derivative of that, right? If a equals b, the derivative of a equals the derivative of b. So we did natural log, we took the derivative, it allows us to isolate y prime, but isolating y prime because we know that y is equal to x to the x, so y prime is equal to x to the x prime. So you end up with this happy thing right here. For example, on this one, our indeterminate forms that we've been dealing with have been 0 over 0 and infinity over infinity, right? It's not a quotient, so you don't see it. But can you quite easily write this as a quotient, Ray? Yeah, you can change this to the limit as x goes to infinity of what? X over e to the x. And now suddenly does L'Hopital's rule apply? Yeah, so this is, L'Hopital's rule is going to tell us that this is equal to the limit as x goes to infinity of 1 over e to the x. And what is that equal to? That is equal to what? 0, because the top stays static. You can just actually take the separate limits now, right? The point is sometimes the fact that you can use L'Hopital's rule is not immediately apparent, but you can do some manipulation and end up with 0 over 0 or infinity over infinity. Okay, so this brings up a second point here. I love it when things battle each other out and you end up with these really cool answers like pi or 7 or 4. There's other random out of thin air things that happen all across math. Even it came up in Algebra 2. So for example, if I asked you to do this right here, to say factor that, you would just say, oh, it's x plus 2 times x plus 3, correct? Another way to explain this is you can break it apart into this, and then what factoring method can you use? What am I doing? What method is this? This is called factoring by what? This is called factoring by grouping, right? Yeah. And you end up with this, right? It's the same thing, right? What was the magical kind of out of nowhere step?
You separate
this thing right here, right? Yeah. Like that's the magic, right? Because how many different ways can you separate 5x? In many different ways. There are random steps in the world of math where you break something apart into one of its infinite divisions and all of a sudden it's helpful. There are random steps in the world of math where you add and subtract the same thing, thereby not changing the value of the expression, but you end up with something you can manipulate. Yeah, I mean, we do something like that with Taylor series, right? We take something that looks clean, runs us into a wall, we blow it up into something that's disgusting, but what can you do with that disgusting thing? Algebra. It cancels out, and then you're done. Now, I was trying to come up with a good segue, but, you know, I I put enough space. I thought I'd get to the segue, but you know, I love factoring. I love these random steps. It should kind of make you feel like this. Apparently, this just got emailed out to the whole school, so it just came up in class like right now, so I had to put it over there. So we'll keep going here. There we go. Okay, I tried to space it out properly. I tried to. Okay, so getting back to where we are right now, there are other questions though that aren't so apparent. So for example, let's look at these four right here. So that here are four expressions that aren't necessarily in forms that you think you can use L'Hopital's rule on. So for example, let's look at A right here. A is the limit as x goes to 0 from the right, and it's from the right because you can't throw in negative numbers into natural log, of x ln x. So we're going to do something that's one of those random steps that makes it look worse, but it puts it into a form that we can work with. X ln x is not a division. We need some sort of division in there, right? Anybody want to guess how we're going to force the division to appear? Yeah, James.
We're going to divide it by 1 over ln x.
Well, we're not really going to divide it by 1 over ln. We have to keep the overall value. We're just going to rearrange x ln x. So how can we rearrange x ln x into a division, not changing the overall value of the expression?
ln x over 1.
Ln x over what? Over 1 over x, right? That is the same thing, right? Do you agree?
Yeah.
That is the same thing, right? Dividing by 1 over x is the same thing as multiplying by x, right? But what happens as x goes to 0 from the right here? So what is the limit as x goes to 0 from the right of ln x?
It's negative.
Negative infinity, right? What's the limit as x goes to 0 from the right of 1 over x?
It's positive infinity.
Yeah, and is it negative infinity over positive one of the indeterminate forms? Yeah, so one of the things you can force a division to appear. You can force a division to appear. So
we don't know what to do.
exactly, so now you can apply L'Hopital's rule. So what about this one right here? The limit as x goes to infinity of x to the 1 over x. What do we do here? No, ln of y is equal to 1 over x ln x, right? So what you can actually do to this is you want to take, so you're trying to find, where is it? Y is equal to that. You can take the limit as x goes to infinity of both of these things. So if two things are equal, the limit as they approach the same thing should be the same, correct? So the book skips around a little bit, so I'm going to try to do out all these things, and sometimes I run into a trap. But limit as x goes to infinity of ln y is equal to the same thing as the limit as x goes to infinity of what?
1 over x.
1 over x ln x, right? So you can actually, so you can't do the one on the left, right? Because there's an x goes to infinity of y, but what can you do with the one on the right? So now look at the one on the right. The limit as x goes to infinity of ln x over what? Over x. When x goes to infinity, what does ln x go to? Infinity. As x goes to infinity, what does x go to? I just said that one too many times, right? So what can you actually do on the right-hand side here? You could do L'Hopital's rule on this, right? Right? You can do it proves dominance. Yes, this proves dominance. You'll notice that we did not prove L'Hopital's rule. I'm not so up on the proof, so I didn't teach it. But what if you do L'Hopital's rule at this point? What does derivative of ln x equal? 1 over x, and this goes to 1. Is that correct? Excellent. So as x goes to infinity, what does this go to? 0, right? So what have we just said? We just said that the limit as x goes to infinity of ln y is equal to what? Is equal to 0.
So
What does that say about the answer?
The limit goes to 1.
Does the limit go to 1? Yeah, what's the only way for ln y to equal 0? 1, yeah. So here's the thing. So y, so therefore what does y, so what does that tell you? Be specific. Does it tell us y equals 1?
No.
It tells us that
1 over x.
it tells us
The limit is x goes to infinity.
the limit as x goes to infinity of what?
To x to the
1 over x is equal to what?
1. 0. I mean 1.
1.
Yeah.
Are we good with that? Does that kind of make sense? The point is, so there's different ways to explode these. There's different ways, the same thing as the limit as x goes to 0 of what? Sine x minus x over x sine x.
Yeah.
And yes, both of the numerator and denominator both go to 0. So can you apply L'Hopital's rule? Yes, you can. Okay, so this is, first of all, what was that first task? I think some of you figured out. Yeah, you need to set y equal to 1 plus 1 over x to the x. So ln y is equal to ln x ln of what? 1 plus 1 over x, correct? Did I do that right? Yeah? So what next? What do I do now?
Take the limit.
Yeah, take the limit. Yeah. So now you're doing the limit as what goes to what? X goes to infinity. That's right. Of ln y is going to be the limit as x goes to infinity of x ln of 1 plus. But there's no indeterminate form yet. So what are we going to have to do? What was that term we made up? Forced what?
Forced division.
Forced division, right? This is going to be equal to the limit as x goes to infinity of ln of 1 plus 1 over x all over what? 1 over x. And as x goes to infinity, what does the top go to? 0. And what does the bottom go to?
0.
This is, you have a L'Hopital check here, right? It is an indeterminate form. So what can you apply? So if we apply L'Hopital's rule, we're now looking at the limit as x goes to infinity. The derivative of the top, we have to make some more space here. What's the derivative of the numerator going to be? Yeah, 1 over what? 1 over?
1
plus 1 over x, right? Times what? What do you have to put in? What do we now have?
1 over derivative.
The derivative of that thing, right?
Yeah.
What is the derivative of that thing?
Negative x.
Negative x to the
Negative.
-2. Are we okay so far? Did I do that okay?
Yeah.
Over what?
Negative x.
Negative x to the -2. So we're going to pause here. Okay. So what do we end up with? The limit as x goes to infinity of what?
1 over 1.
It's just 1 over 1 plus.
And that goes to 1.
And what does that go to? 1. So what does that tell you? The wrap-up is really important. It tells us the limit as x goes to infinity of ln y is equal to what? 1. So therefore, y is equal to e. And what did we say y was equal to? This thing. So we now know y, this thing, the limit as x goes to infinity of y is equal to e, so therefore it's equal to e. There you go. So what was this thing? We'll give it a term right here. What was this called? This was called forced division. How do we feel about that? You go forward how much? 1. You go to the right, 2, and then you go up 3. When you draw these axes, I highly recommend avoiding 45 degrees. Why do you want to avoid why do you want to avoid that? So when I say 45 degrees, if I draw these at exactly 45 degrees, that's not exactly 45. There are certain degree angles when you draw them, it loses some of its perspective. It's harder to see the perspective. I recommend more like 30 or 35 degrees. So right here, that would be 45 degrees and this would be 45. I recommend sliding this up a little bit like they did on these diagrams right here. You see how they go the other way. They slide it down. So what about this point right here? 0, 0, 1. That means how far on the x-axis do you move? None. How far on the y? None. That means you just go down 1. The red here, these are all the positive directions. These are all the positive directions. So if these are the positive directions, what happens if you go the other direction? The negative. Exactly. Right. Some of the things we do are going to get, some things are going to get broken. So for example, this one, the three-dimensional Pythagorean theorem is exactly what you think it is. Okay? It is. It's great. Other things get broken. So for example, points on a three-dimensional surface. So for example, if I have a parabola, what's the concavity at this point? Concave up, right?
Yeah.
Well, you can have in 3 space, you can have points that are concave up and concave down at the same time. Really cool, right? Saddle points. So certain things will change, certain things won't. But this is a diagram where you can prove the Pythagorean theorem. Okay.